You're ready, please take it away.
Okay, it is clear enough? Okay. Hello, I'm Sunho Park. Today I'm going to present my work on a proof recipe for linearizability in elect memory separation logic. First of all, what's linearizability? Linearizability is a strong correctness condition for concurrent data structures. Let's consider a concurrent trace where 3 threads are accessing a concurrent stack at the same time. In this situation, the linearizability of a concurrent stack guarantees that there exists a linearization point within function execution such that the linearized execution satisfies the sequential behavior of the stack. And this simple idea has been captured by the logically atomic triples in separation logic. The key idea of it is that at the linearization point, we make an atomic transition from the resource in the precondition to the resource in the postcondition. And it is well known that these logically atomic triples imply linearizability. However, the problem is that this simple style of specification is not applicable to elect memory because it is too strong to describe all the elect behaviors. I elaborated about it using the same example as before, but now in elect memory consistency. In elect memory consistency, each thread may not read the latest value stored on the memory. As a result, the second thread may fail to pop anything from the stack. In this scenario, the linearized execution does not satisfy the sequential behavior of the stack. So to explain this behavior, we have to consider the reordering between events. In particular, if we reorder push 1 and empty pop as shown in the screen, then you can easily see that the linearized execution now satisfies the sequential behavior of the stack. So in summary, the lesson from this one is that in elect memory consistency, we have to consider the event reordering. However, this event reordering should not happen too much. Consider this another example where one thread executes push and then pop. In this case, these two events have a very strong causal order between them, so the reordering between them should be forbidden. And by forbidding this reordering, we can now guarantee that the pop operation should succeed in popping out the previously pushed value. So the lesson from this example is that event reordering should not happen too much, and it should observe the causality between events. These two lessons have been already considered by our prior work on a new style of specification called linearizable history specification. The key idea of it is that we maintain the history of all the events that have happened so far. And using the history, the specification guarantees that we can reorder some events in the history to satisfy the sequential behavior of the data structure without violating the causality. And it is well demonstrated that this specification is very strong in the sense that it can be used to verify a large set of clients that uses very complex pattern of synchronization. Now, it is time to focus on the remaining problem, which is that this style of specification is very difficult to prove in reality. There are several data structures that have been proven correct in elect memory consistency. And we found that to verify data structures in elect memory consistency, we have to spend about 10 times more proof effort. So as a result, some data structures are only verified against weak specifications, and some data structures have not been proven yet. In this situation, our main goal is to reduce the proof effort and increase the scalability of the proof. To achieve this, we first propose a proof recipe for manual verification of the linearizability. And on top of that, we apply proof automation technique to further reduce the proof effort. By combining our two proof recipes, we were able to reduce the proof effort by about 81% compared to the prior work. Consequently, we were able to verify more data structures against the strong specifications. And we were able to verify Meta's Folly library for the first time in elect memory consistency. If you consider our work in perspective of proof automation, then it turned out that our work is our first work on the proof automation of the linearizability that supports elect memory consistency. So to achieve our goals, there were 3 major challenges in proof structure and compositional verification and proof automation. And due to the time limit, we are going to only focus on the first 2 challenges. For the first challenge, I will explain it to explain our new proof structure. let's gain some insights from simple invariants in a simple setting called sequential consistency. We will do it using a simple example called Krebbers stack, which is a very well-known concurrent stack that is implemented as a linked list structure. The invariant of Krebbers stack is very simple. As shown in the screen, it basically maintains a very strong and intuitive connection between physical state and logical state. And here, you should notice that you should remember that this simple, strong connection between the two states plays a key role in easy invariance and easy reasoning principle. We will see why it is so effective by going through a concrete, high-level verification of Krebbers stack. Let's consider the push operation, where we first read from the head pointer, and then we allocate a new node containing the value, and then we set the next pointer of it. Finally, we update the head pointer using atomic instructions like compare and swap. In this case, at the last step of the operation, we update the physical state. And as soon as we update the physical state, we should also update the logical state following our simple invariant. And here, the update of the logical state can be done very easily because thanks to our simple connection between physical state and logical state. The same story holds for successful pop operation like this. One interesting case is the empty pop case, where we try to pop from the empty stack. In this case, the empty pop case is considered as a read-all event because it does not change the physical state. And thanks to our strong connection between physical state and logical state, we don't need to update the logical state in this case. And in other words, this means that in sequential consistency case, in sequential consistency memory, we have the proof obligation to verify empty pop case is very easy because we don't need to update the logical state. Now, we are going to consider the same example, but now in relaxed memory consistency. The high-level proof structure is the same. We are going to construct some kind of connection between physical state and logical state as we did before. However, the physical state is a little bit complex when comparing to the sequential consistency case because we have to remember the history of all writes to the memory in this case. The logical state is also complex because we have to remember the linearization order of all the events that have happened so far. In this setting, we are going to go through the high-level verification step of the Krebbers stack as we did before, and while doing this, we are going to find out what's the problem in relaxed memory consistency. The push operation proceeds as the same as before, and the verification of push operation is the same as before. At the last step, we update the physical state, and then we update the logical state at the same time. The same story holds for successful pop operation. However, the main complication comes from the read-all event. In this case, we should consider the empty pop case. To see why empty pop case is the main complication, let's see that the read-all since empty pop is read-only, we do not update the physical state. However, in contrast to the sequential consistency case, we should now update the logical state in this case because this new empty pop event should be inserted within the linearization order. This means that read-only events can be inserted without changing the physical state. In other words, read-only events have only the weak connection to the physical state. And this weak connection is a main enemy in proof simplification because this means that for a given physical state, there can be a lot of valid logical state that contains lots of read-only events. So this is the main problem that we want to solve for the first challenge. To solve this problem, our main idea is that it is okay to focus only on the right events when establishing our invariant. This main idea has been we encoded this main idea into our new proof structure called object modification order, or in short, we call it OMO structure. The OMO structure basically maintains the total order of only the right events, and the read-all events are just placed below the corresponding right event. And using this object modification order, it is now possible to set up a strong connection between physical state and logical state by only considering the right events. So in short, So as a result, we can the simple invariants are now possible by only considering the right events. Furthermore, since OMO structure is a specialized structure for dealing with readable events, we designed several proof rules. That is very easy, and these proof rules contributed to reduction of the proof effort a lot. So far, we have discussed our new proof structure called OMO structure that enables simple invariants and easy proof rules by focusing only on the right events. Now, we are going to apply this new proof technique to a more complex situation where we are going to verify a complex data structures in a compositional way. When discussing about to discuss about compositional verification, we are going to use elimination stack as a running example. Elimination stack is another implementation of a concurrent stack, and it uses traverse stack and exchanger as low-level modules. Each operations first make a function call to the corresponding operations on the traverse stack, and if it fails due to the race condition, then it now uses exchanger as a side channel to atomically exchange the two operations between push and pop. And using this example, I'm going to present how we can verify this elimination stack in a compositional manner. In other words, we are going to construct the OMO structure of elimination stack by only looking at OMO structures of lower-level objects. To simplify the proof effort, in this compositional verification, the key idea is that we exploit structural similarity between upper-level OMO and lower-level OMO. And let's see the structural similarity by going through a concrete example. To see the structural similarity, we are going to connect every upper-level event to the corresponding lower-level event using our new relation called the committed relation. Committed relation basically connects the two events whose linearization point coincide. In this example, suppose the push operation of the elimination stack has just been finished by only executing the push operation on the traverse stack. In this case, the linearization point of the upper level push event comes from the linearization point on the lower level traverse stack event. So we connect them using our new relation of committed relation. We can we can continue to establish this relation, and up to this point, we can see that this relation usually satisfies monotonicity. And this monotonicity is very important because it allows us a new viewpoint that the lower level OMO can be viewed as a projection of upper level OMO. This is the structural similarity that I want to exploit. And this is very effective in proof simplification because it allows us to project very complex proof obligations on the upper level OMO to the corresponding and very simpler ones on the lower level OMO. I'm going to elaborate about it with another concrete example. Consider the case where we are going to insert a new empty pop event. In this case, we have to prove the validity of the reordering regarding this empty pop event. And to do this, we can exploit the monotonicity. First, we consider the proving the validity of the reordering with push 1 and push 3, which are connected to the traverse stack event. In this case, we can directly use the monotonicity to project the proof obligation on the upper level to the corresponding ones on the lower level. And you can see that the validity of the reordering on the lower level is already guaranteed by the specification on the lower level object. So we can immediately finish this proof obligation. So all we need to do is proving the other part of the proof obligation. And for that part, we can do a very different kind of reasoning. But due to the time limit, I'll just skip it. And if you're interested, then you can find more details in our artifact. So to conclude, we propose a proof recipe to reduce the proof effort and increase the scalability of the proof when proving the linearizability in linked memory consistency. Our method was able to reduce the proof effort by about 81%. And in our paper and artifact, there are more interesting discussions about concrete resources, proof rules, modification of the style of the specification, and also the proof automation idea that uses diaphragm. All our work has been formalized on IRC11 separation logic on Coq. So if you're interested, please visit our GitHub repository to see more information. Thank you so much, and I'm now happy to answer your questions.
Okay, thank you. If you have a question, come up to the microphone. I'll ask one or two questions in the meantime. So my first question is about this OMO data structure that you use. So you essentially have the writes ordered in this this sequential way, and then the reads ordered as attached to a particular write, right?
Yes.
So can I generally think of that as sort of a partial order, or have you thought about using partial orders to model the history instead of sort of sequential relations?
Actually, it is not a partial order because as this arrow is shown as a one-directional, in reality, we can do it in a bidirectional way. In other words, you can construct the total order from this structure. This exploits the somewhat very complex, interesting property that you can believe that this structure is a two-dimensional high-level structure that maintains the linearization order. So it basically makes a total order in this way. But in a high-level structure, we basically only consider this total order. This is the key point, and this is not a partial order structure. Yeah, I should mention it.
Okay, I guess what I'm saying is, like, for example, you could think of the empty pops as only depending on the init. They don't really depend on each other.
In reality, they may have some dependency, but actually, readable events have very less effect on the global memory. So we can do this kind of structural optimization, like I say, yeah.
Okay, I'll have to take that. I'll take that one offline. I'll ask one other question then. So you mentioned the results you had in verifying a number of concurrent data structures looked very impressive.
Yes.
I was wondering if you foresee any challenges to extending those proof verification efforts to other data structures. Is it sort of like, are there challenges to the reusability of the proof infrastructure that you've developed?
Okay, that's a good question. And actually, already in our paper, we tried to verify a very large set of concurrent data structures, and also as a follow-up work, we are currently going through a verification of more complex data structures, like very complex hash maps or something like that. And currently, we are seeing that this can be easily adopted in highly complex data structures. Because it is very general to the concept of the linearizability in elect memory consistency. So yeah, in conclusion, yeah, I think it can be easily adopted to other kind of verification.
Okay, very nice. Okay, so if there are no other questions, let's give our speaker another round of applause.